Hey mathematicians, here are your notes for 4.6. Still talking about functions, day 2. I'm going to skip over the bell work. It is the exact same as yesterday, but I'm going to continue to really push that into your mind, the definition of a relation versus a function. If you want to add the definition of a function there instead, you can do that too. But the goal for the day is to be able to recognize something called function notation and be able to interpret functions. So quick history lesson. I think the history of math is absolutely amazing. So Leonhard Euler, like I said, Euler, created a special notation or a way of writing functions. Instead of using y equals, he replaced it with f of x. That's how this is said. Now why would he do this? Well, a function works like a machine. A function is given a name that can be any letter, such as f or g. The same thing that we would use kind of for our variables, we can use for function names. Again, we stay away from things like O and S because they can sometimes be confusing. The notation f of x represents the output when x is put in. So when x is put into the machine, f of x comes out. In this notation, f of x replaces y. So example, y equals x plus 3 is the same as f of x is equal to x plus 3. So y is equal to f of x. Now I'm going to take just a minute to show you why I personally like this notation. I know it can be really confusing for some, but this is what I like about it. If I'm given a domain, x equals 7, and I put it into a function, and that function kicks out y equals 6. This is just an example. My final answer is y equals 6, and I can circle that, and the person who is grading or who is looking at my research, whatever it is, whatever context, only sees y equals 6. They may not see what was put into the function in order to kick out an answer of y equals 6. The other thing I don't like about this is if I were to try to create an ordered pair right now with my solution, I would only have one variable. I wouldn't have the other one. What I like about function notation is that when I have something like this, where f of x comes out to 6, what I can do, and what you'll see in a lot of research, is function notation is used to say when I plug in 7, when I replace x with the number 7 in the function, and I plug it in, we'll see that in a minute, it equals 6. These say the same thing, because y is equal to f of x. However, the reason that I like this notation a lot better is that if I were to be able to create a solution set or an ordered pair, I would know exactly what I plugged in and exactly what I got out. This gives me one piece of information, this gives me two. That's my personal preference on it and why I think it's really useful. So let's jump in and see that a little bit more. It'll probably make more sense as we go along. I basically restated this. I wanted to explain it a little bit differently, but why is this useful? If you write y equals 3, you only know the output. If I write f of 1 equals 3, you know the output of 3, but you also know the input, which is 1. So now, what about the machine thing that I was talking about? Well, when numbers are put into the function machine one at a time, the function performs an operation on each input to determine the output. So in my last video, when we were plugging in a domain and getting out a y, getting out that range, that was essentially a function at work. We just didn't necessarily call it a function at that time. So for example, when x equals 3 is put into this function, f of x is equal to x squared minus 1, the function squares 3 and then subtracts 1 to get the output, which is 8. So an example of this, let's see if we can take this and put it into practice. This example says find the output for the function f of x equals x squared minus 1 when the input is x equals 4. Another way of writing this is find f of 4. So, in my function, I replace the f of x with 4 because 4 is my x. Then what I'm going to do is anywhere I see x on the right side, the same way that I replaced it on the left, I'm going to replace it on the right. 4 squared minus 1. So now I have input, I put it into my function, and I solve. 4 squared is 16, 16 minus 1 is 15. So my function, f of 4, is 15. Notice, I'm not calculating with that left number. All the left-hand side, all the function notation tells me is that 4 was my original input and 15 is my output. If I want to say find f of 4, this is a perfectly okay solution, but again, I like to put it into that ordered pair the way that we're used to. Because again, it gives me 2 pieces of information, I might as well use both of them. Notice I did not divide by 4 on the left side, I did not multiply, I did not subtract, I did not add. That is the number one thing I see students do, is they get to this point and they say, oh, I've still got a number over here, the f isn't by itself. Remember, f is not a variable. We are not solving for it. We're solving for the entire left-hand side because this is equal to y. All right, let's see another one. Calculate f of 1. Meaning, when I say that x is equal to 1, and when I plug in 1 for x, 1 squared minus 1, I solve 1 squared minus 1 is 0. So f of 1 is 0. My input to the function machine was 1. My output was 0. Just like that. Let's see another one. Calculate f of negative 1. That means I'm plugging negative 1 into my function. So I plug it into my equation. Negative 1 squared is 1. 1 minus 1 is 0. F of negative 1 is 0. My input was negative 1. My output was 0. Therefore, my answer is negative 1 comma 0. This is just plugging numbers in the same way that we did in our other video. I'm given x, I need to find y, except now I'm using this function notation. Practice, practice, practice. You'll get it. Jumping to the back, the next thing we're going to talk about is something called composite functions. Composite functions mean that the output of one machine becomes the input of another. So the same way that we don't just take cotton from the field and turn it into a t-shirt, there's steps in between. We have to make it into thread, and then we have to make it into fabric, and then we have to sew it together. So think of this as each of those steps of manufacturing something like a t-shirt. So for the example shown at right, my f of x function, notice that's my first function, is equal to 3x plus 1. My second function, g of x, is equal to 2x plus 4. Right there. So a problem may ask you to solve for something that looks like this. This is really big, but please do not be concerned by it. I promise it breaks down simply. In order to do so, you must plug your value into the first function, in this case the f of x, and then once you have done so, your output, so whatever answer you get, becomes the input for this function. So let's calculate the following. Identify your inputs. The easiest thing, or the thing to make these easier, is to remember that parentheses work from the inside out. So work from the very inside towards the outside. So this function is g of f of 0, meaning I need to find f of 0 before I can find my other functions. All right, let's do that. I know that f of x is equal to 3x plus 1. Therefore, if I plug 0 into that function, it's the same thing as saying 3 times 0 plus 1. I solve for that. 3 times 0 is 0, plus 1 is 1, and I get f of 0 equal to 1. Now notice, the same way that we can plug in 0 for x to replace that, we have an f of 0 inside of our g. If we know that f of 0 equals 1, we can rewrite this function as g of 1. All I've done here is replace the f of 0 with 1. If they're equal, I should be able to legally do that. The nice thing about this is I know it's true because right here it says, once you have done so, your output, or number 1, becomes, your output because, this is supposed to be becomes, let's fix that, becomes the new input for the function. So my output becomes the input. So I've done that correctly. Alright, same thing, I have g of 1, so I have to solve for that. G of x is equal to 2x plus 4. If I'm replacing x with 1 on the left side, I need to replace x on the right side with 1 as well. 2 times 1 plus 4. Solve. 6. G of 1 is equal to 6. However, remember, this isn't where I started. I didn't start with g of 1. I started with the function g of f of 0. And I know that through my process, it equals 6. It's a long composite function, but this is your final answer. 0, 6 would also be correct. However, when I'm working with composite functions, I prefer to write the entire final answer like this because it indicates that I went through more than just one function step. I went through multiple steps. Alright, if you're feeling confident with that, go ahead and do the next one on your own. If not, that's okay. We're going to work through it together. Again, I'm going to work from the inside out. I need to find g5 so that I can replace that with a number later. This time, I'm not going to start with the f of x function. I need to start with the g function. I'm going to plug it into that function the same way I have been. That would be 14. So g of 5 is equal to 14. If I replace g of 5 in here, I get f of 14. My output becomes my new input. And then I calculate again. F of 14 means that the x in this function gets replaced with the number 14. This is my x value, my independent variable. And I'm going to plug it in just like that. And then solve. 14 times 3 is going to be 42. 42 plus 1 is 43. So f of 14 is 43, but again, that's not where I started. I started with the function f of g of 5, and my final answer is 43. So I just did that function machine 2 times using that output. Alright, last one. I know this video is kind of long, just bear with me, we're almost done here. The distance d of t, notice they're all read the same way, it's only the letters that change. So it could be f of x, g of s, whatever. In this case, it's d of t. Represents the distance, notice the distance is the y, when t, the hours into his, I'm sorry, I should just read this properly. Represents the distance Gulliver is from home, t hours into his trip. So t is the thing that we are changing, or looking at, I guess. He could change how far into his trip he is. So that is what he can control, meaning t is his x value. His distance, he cannot control, because the farther in the time, you can't get less distance. So we would write this as t with where, excuse me, let me rephrase that. T is the x value, and d of t is the y value. So that might help to look at as we're doing this problem. Our first one says use the graph to evaluate the function at each value. So d of 2. These ones I think are pretty simple because these say when your inside value, when your t is 2, what is your distance? What is your d of t? And because we have a graph, we don't even have to plug numbers in. We can just go right over here. Let me see if I can Oh yeah, there we go. Let's shed some light on it. So if t is 2, based on the function given, his distance, let's put some lines in here, is 4 miles. So d of 2 is equal to 4 miles. D of 5 says that if t is equal to 5, what is your y value? What is your distance? Well, when t is 5, we go over here, we say our time is 5, and at that time, our distance is 11 miles. Notice I'm not plugging numbers in, I'm just using what the graph tells me. When your time is 2.5 hours, it's right here in the middle, right there, that would be 4 hours. So d of 2.5 is 4 hours. I don't care how you write it, I'm just showing you some steps in between that help me. And then of course when distance is equal, when time is equal to 10, his distance is 0 because he's back home. He's 0 hours from home. At one point he was 11 hours from home. So that's not too bad. That gives us t and asks us to find the distance. Reasonable. This one is where people get confused. This one says calculate the value of t, meaning find the x value when given the y. Calculate the value of t that makes the equation true. Do not plug in the number given as you did in the previous problem. Remember that when using function notation, f of x equals y. So the number one problem I see is that people say, oh, d of t equals 2. They go over and find 2 on time, and they say it's 4. That is not true, because this is not t equals 2. This is d of t equals 2, meaning y value. So while up here we went on the x-axis and found our corresponding y value, with this one we need to find our y value and then find the corresponding x. So let's do that. If your distance is 2 hours from home, we find 2 hours on the y piece, and then we curl across and say, well, how far in time was he? Now the first obvious one is 1 hour from home. But what I'm going to tell you is that if we keep going over here, he could also be over here. We don't know. It doesn't specify whether he was closer to home or farther from home. So we actually have two answers. My t could equal 1 hour from home, or my t could equal, what are we going to say there, 9.3 hours from home? 9.3 hours into his trip, I'm sorry. Now notice, these are not repeating y's. They are two completely separate x values that have the same y. And as we said yesterday, that's totally legal. If I was to write these in the form of a coordinate point, I would see that I have repeating y's, but not repeating x's, meaning that is legal. All right, try that next one on your own, and then come check it. All right, distance is equal to 5 miles. So I go and I find 5 miles into my trip, and I say, well, at 5 miles, he was either 4 hours from home, or he was, where would that be? 8.5. So t is either 5 or t is 8.5. It could be either one. Again, as I've been saying, there's not always only one solution. Sometimes we have two, and if that's the case, we do have to write both of them down. Functions are super useful, and they're super important when it comes to algebra and other math. That being said, I know that they can be challenging, so if you have any questions, please don't hesitate to let me know. I would be happy to clear up any confusions.